Hello again! I hope you benefit from my playlist of tutorials on functional safety in vehicles. This is another video for experts on functional safety. Today I will talk about the so-called HARA, which stands for Hazard Analysis and Risk Assessment. This important step in ISO 26262 defines how the risk posed by electronics in road vehicles should be estimated and assessed. In particular, it's about the risk of electrical, electronic and software systems malfunctioning. You will hear about the 8 most important aspects that you need to consider when conducting a HARA. My name is Erwin Petri. I give training courses at Kugler Mark on functional safety in the automotive sector. I advise companies on this topic and assess the functional safety of automotive products. So, electrical and electronic systems in vehicles must be safe. To develop safe software and hardware, for example, you must first ask yourself what could happen if the software or hardware fails. In classic risk management, you then assess the probability of certain risks occurring and the severity of the consequences. From this, you derive a risk assessment and an approach to dealing with risks graded correspondingly. It has turned out that this classic approach to risk management is not easy to interpret and implement within the context of electronics in road vehicles. Instead, what is needed is a special approach so that the procedure can be adapted and reinterpreted. This is precisely what is described in ISO 26262, the standard for the functional safety of road vehicles. In this video, I will explain this procedure and give you a number of practical hints and useful tips. I will then summarize the most important points for you. You will need to keep these key lessons in mind for your future work. Before we turn to the HARA procedure, we need to understand what a HARA is for. The term Hazard Analysis and Risk Assessment refers specifically to the procedure defined in ISO 26262 for the automotive sector. It is abbreviated as HARA and is defined as follows. Method to identify and categorize hazardous events of items and to specify safety goals and ASILs related to the prevention or mitigation of the associated hazards in order to avoid unreasonable risk. Phew. Easy, right? Not quite, I guess. There's a whole lot of special terms used in that definition. We'll go through the terms in this video. Please note that in the automotive sector, you always use exactly this HARA term and this designation because it precisely describes the prescribed procedure. For example, if you used the widely used term hazard and risk analysis, other people would probably think you mean the requirements contained in IEC 61508, which are not specific to the automotive industry. First of all, a comment on the term hazard. This refers exclusively to hazards that can lead to physical injury or damage of the health of persons. Damage to reputation or costs for car manufacturers and their suppliers are not included in this analysis. So, the definition refers to items to which the HARA is applied. This means that such a HARA is applied to functions on a vehicle level and to the systems that implement these functions. Examples: steering, braking, automatic cruise control, driving lights. Since we have a number of such items in a vehicle, the same number of HARAs must be performed. You can imagine that it's not easy to separate items from one another and that this creates a lot of work. Car manufacturers have to compile lists of items for vehicles and know how they relate to one another. They are therefore responsible for implementing the HARA, not the suppliers. The definition of HARA also refers to avoiding unreasonable risks. Unreasonable risks, in turn, are to be interpreted as risks judged by society to be morally unacceptable in a certain context according to valid societal moral concepts. This now makes it difficult since there are no such things as objective assessments in this area, or not in any way that can be used as a benchmark. As we will see in a moment, ISO 26262 does contain concrete criteria, but in the case of HARA, these have to be interpreted by car manufacturers, so they will depend on the context. This can lead to different results from a HARA. For example, criteria could depend on what use vehicles are put to, target regions, or the skills of average drivers. To a certain extent, ISO 26262 takes this into account by including special interpretation tables for cars, trucks, buses, and motorcycles. Ultimately, a HARA depends on the people who carry it out, however, despite the specifically prescribed method. To prevent misinterpretation and cheating, ISO requires HARA reviews and confirmation from an independent body. How does such a hazard analysis and risk assessment work in practice? To explain this, I divide the HARA into 7 logical steps. You can start with the first step by basing it on an existing item definition. In the first step, you determine relevant operational situations and operating modes. Operational situations could be, for example, driving in the city, on a country road, or on the motorway. Operating modes could be, for instance, driving forwards, reversing, or even jacking up a vehicle in a workshop with the engine running. Which subcategory of operating situation or mode needs to be considered will depend very much on the respective item. The second step is to imagine risks to life and limb. You should write down any hazards that could arise either from a fault in the item or from reasonably foreseeable misuse by a driver. Hazards to passengers and other road users have to be determined on a vehicle level. One example of a danger posed by adaptive cruise control is unintended acceleration. Or the driving lights present a hazard if they go out unintentionally. How the item was designed or made is not relevant. But if a fault in one item leads to the failure of another item, then you must consider the dangers involved. A certain hazard occurring in a specific operating situation is now called a hazardous event. For example, if the lights go out while driving in the dark on a winding country road, that would be a hazardous event. In the third step, these hazardous events are then evaluated individually according to 3 criteria. These are the severity of any potential injury, how frequently an operational situation arises, the exposure, whether a situation can be managed to avert injury, the controllability. The severity of injury is assessed in 4 stages. ISO 26262 defines these levels by referring to the abbreviated injury scale or AIS classification. 5 levels are defined for exposure. There are also 2 approaches to rating these. One classification, the frequency of an operational situation arising, is a suitable option for errors that may occur in certain situations. This could be something like an airbag failing during a collision. You're not going to notice that an airbag won't trigger during normal driving situations. Classification according to duration is always used if a fault would have an immediate effect. For example, this could be the lights going out during nighttime driving. In such cases, you would estimate the typical percentage of vehicle operating time at night compared to overall vehicle operating time. For a passenger car, the assumed operating time is often 400 hours per year. But you have to estimate this for the vehicle in each individual case. If the element that may fail is a control unit and it's in permanent use, you don't take the vehicle operation time as a basis for estimating percentages. It's important to understand that exposure is not about estimating the frequency with which a fault can occur. It's about estimating how likely you are to encounter a situation in which an error may have an impact. Controllability is about assessing to what extent people in danger can still avoid injury by reacting in time in the event of a malfunction. According to ISO 26262, 4 levels of controllability are distinguished. Please note that it is usually, but not always, the driver who is expected to react. For example, maybe a pedestrian could jump out of the way to avoid being hit by a vehicle. When we look at the definition of controllability, we are talking about the abilities of average drivers. In concrete terms, this means you actually have to define what average drivers are to assess their abilities. Unfortunately, I cannot give full details of the severity, exposure and controllability criteria in this video. Part 3 of ISO 26262 provides precise definitions of these, plus a number of examples and tips. In addition, the appendix to Part 3 contains special notes on the exposure for trucks and buses. With motorcycles, all 3 criteria have to be interpreted differently, which is why Part 12 provides special examples. You may now ask yourself whether there's a standard assessment for the 3 criteria to make life easier for everyone. Well, yes, there are examples of such assessments out there. For example, there is VDA 702. But such documents only ever provide examples. They are not binding. This is for the simple reason that vehicle manufacturers remain responsible for assessing individual circumstances. Their obligation cannot be delegated to other parties. Similarly, there are no binding lists of hazardous events for individual items, even though vehicle manufacturers and their suppliers compiled such lists a long time ago. If you're conducting a HARA for the first time, you will find that you have to approach a sensible number of hazardous events iteratively. As a rule of thumb, you can remember that you can combine several hazardous events if you come to the same assessments of the 3 criteria. We've now reached the 4th step of our HARA. For this step, you determine the Automotive Safety Integrity Level, or ASIL, for each hazardous event. You can do this quite simply by looking at this table, which has 3 estimated values for S, E and C and provides you with the ASIL. Worst case scenario, you have a hazardous event that can result in fatal injury, S3. Vehicles are often in an operating situation where this can happen, E4, and injury can be avoided in less than 90% of cases, C3. Such an event will receive ASIL D, which means the strictest ISO 26262 requirements must be applied to prevent the event happening. The table highlights an important principle. If one of the three criteria is given a rating that is one level lower, the overall ASIL is reduced by one level. For example, if we assume that more people can still avoid injury by reacting in a certain way that is rated as C2 and not C3, so the dangerous situation only receives ASIL C, and so on. The QM classification shown in the table allows you to keep developing the item without ISO 26262 based solely on the standards of automotive quality management. For motorcycle development, apply the same procedure except that the result is called a Motorcycle Safety Integrity Level, or MSIL. However, all parts of ISO 26262 specify that any actions taken have to relate to an ASIL, so you will need to use this table to convert the MSIL to an ASIL. You will also notice that this will result in reductions one level at a time. Motorcycles are at the most, therefore, developed using ASIL C. You may wonder why. ISO 26262 does provide a few indications that shed light on this. Motorcyclists wear helmets. Motorbikes are not likely to be ridden at high speed on unpaved roads, and they require a special driving license. The very fact that some people ride a motorbike is already an indication that they are willing to enter into higher risks. Once you have your ASILs for dangerous events, the next step is to formulate so-called safety goals. These are functional objectives or top-level safety requirements, and they must be suitable for preventing or mitigating hazardous events. An example for a safety goal? Prevent an electromagnetic steering wheel locking system from being activated while a vehicle is in motion. In many cases, you can formulate individual safety goals for several dangerous events. Then you end up with a single-digit number of safety goals. Each safety goal is given the highest ASIL for corresponding hazardous events. The primary output of a HARA is a set of safety goals with corresponding ASILs. These provide a starting point for developing a functional safety concept. So now we come to our last steps: verification and confirmation. If you've carried out and documented the HARA, you must subject it to verification according to the rules of ISO 26262 Part 8. A review team must, for example, check whether sufficient and reasonable hazardous situations have been considered, whether this is consistent with the safety goals, and whether the HARA procedure has been applied correctly. The seventh and final step is to have each HARA assessed by a person outside development. You need independent confirmation to be sure you've established the correct ASIL and the ISO 26262 criteria for a HARA have been met. This has taken you through all the steps. Now you know what has to be done and how it all fits together. And maybe now you can see how much work is involved for an inexperienced team going through a HARA for the first time. You have to keep in mind that you will need the input of a variety of people for some topics. Who can provide a list of relevant operational situations? Who can help estimate the severity of injuries linked to different types of accidents at different speeds? What statistics are needed to do this? Does testing have to be carried out with larger groups of people to understand their reactions to certain vehicle failures? If you're conducting a HARA for your company for the first time, it will probably be a highly complex undertaking. But once you've done it for your type of function or product, it will have a steep learning curve, so you can expect it to involve much less effort the next time round. I said at the beginning that car manufacturers must carry out the HARA. As a supplier of electronic solutions, however, it can still be extremely useful for you to carry out a HARA yourself in product development. This will involve making assumptions about the items your component will be used in. A HARA will then provide you with safety goals and ASILs, and these allow you to work out meaningful functional safety requirements with ASILs, providing you with a robust starting point for the scope of required development. This also enables you to develop products without having to define specific customers. And it puts you in a much stronger position later on when you're negotiating with car makers. To a certain extent, it also solves a problem that often arises when car manufacturers leave it too late to tell you about safety requirements. So that takes us through all the points I wanted to make. Let me conclude by summarizing the most important things in 8 key lessons. First, we're only looking here at hazards to the lives and limbs of road users arising from faults and incorrect behavior of electrics and electronics in road vehicles. Second, these hazards must be identified and assessed according to a predetermined method, hazard analysis and risk assessment. Third, a HARA is typically performed by the car manufacturer for items, for functions on a vehicle level. Relevant hazardous events are identified and assessed, covering the severity of harm, S, exposure, E, and controllability, C. And number 5. An automotive safety integrity level, or ASIL, is to be determined based on these 3 parameters, S, E, and C. Sixth, for each hazardous event, appropriate safety goals are set up with the ASILs. You must have achieved these goals by the time you finish development. Seventh, the ASILs, A to D, determine how rigorous each step of development and each safety mechanism will need to be. And one final key lesson: it's a complex process the first time you implement a HARA, and it takes a lot of input from third parties. But afterwards, doing HARAs should become considerably cheaper. So, now you know what it's like conducting a hazard analysis and risk assessment for road vehicles according to ISO 26262, but also what it's needed for and why it's not a simple process. If you'd like to go through all of this separately or perhaps integrate it into your company training program, simply use the link below and download the white paper. If you enjoyed what you saw and are interested in further specialist topics, please subscribe to this Kugler Mark YouTube channel and watch more videos. And maybe you will recommend our videos to your colleagues. See you soon!